Our speaker tonight is Dr. Kevin Birdwell. Dr. Birdwell works as an atmospheric scientist in Oak Ridge, Tennessee. He graduated from the University of Tennessee in Knoxville in 2011 with a PhD in physical geography with an emphasis in complex terrain meteorology, air pollution, and paleoclimate. He also attended Murray State University, where he received his BS and MS degrees in the same field with minors in math and remote sensing in 1988 and 1996, respectively. Kevin also received an AA in Bible from Central Bible College in Springfield, Missouri, now Evangel University. He's been associated with RTB as a volunteer apologist since 1998 and a visiting scholar since 2012. He's also been active in apologetics and church ministry since the mid-90s. He's a licensed minister with the Church of God in Cleveland, Tennessee. Kevin most recently spoke to our chapter in 2016, so it's a pleasure to welcome him back this time. Please join me in welcoming Kevin Birdwell.
So I'm going to try to take you through somewhat of a tour of paleoclimate history and what that implies about how the Earth's climate works, and maybe really with the goal of understanding how that might impact what we're dealing with today in terms of climate change and how we might deal with it. So one of the things that I enjoyed doing as a PhD student was learning basically how to derive information about the climate of the past. And there's a lot of different ways that that's done. Things like tree rings, lake barbs, glacial ice, fossil pollen, speleothems, which are cave deposits, and corals. And they're all useful at different time ranges. My focus was mostly on tree rings because my major professor was a dendrochronologist. And, you know, let's just give you an example here of ice cores. What you can do with ice cores, you can determine paleo temperatures, humidity, snow accumulation, past volcanic activity, how active was the atmosphere, we call it turbidity, wind speed, atmospheric composition, atmospheric patterns, and solar activity from all of these different factors you see listed there. Now, you can't get down to the kind of measurements that we do today where, you know, we know that a high and low temperature occurred on a certain date, but you can get general patterns and trends. And in some cases, you can even get down to seasonal data. And most of this information comes from the stable isotopes of water, trace gases, and sealed bubbles in the ice. In this case, dissolved in particulate matter in the Fernan ice. For example, volcanic eruptions generally have a very unique chemical signature. So when you find that in an ice layer, you can determine that it was a particular volcanic eruption, and you can cross-reference it with other parts of the world sometimes. And then just the physical characteristics of the ice. Beryllium-10 is also associated with heliomagnetic activity, so there's a lot from that we can learn about what was going on outside of the Earth. All right, I'm going to skip a few of these. And the reason I'm bringing up this one about Dead Sea shore layers is because I'm going to reference that later on. But what you're looking at there is basically an 11-meter deposit that represents different ages of Dead Sea shore deposits. And that's very useful because these can all, if there is organic matter in them, they can be carbon dated, and we can determine from these deposits what the lake level was of the Dead Sea, for example, during different times in the past. So in this case, we're covering the period from about 2200 BC, just before Abraham, until close to the present. So in essence, what I'm saying is that we can use the Dead Sea as a rain gauge, as a giant rain gauge, because it doesn't have an outlet to the ocean. It basically goes up and down in response to long-term precipitation pattern changes. All right. Solar cycles are interesting. In fact, they were useful in the beginning of tree ring research because it was discovered that there were patterns in the tree rings that followed the approximately 11-year solar cycle. Even though this is only 0.1% variation, you know, sometimes you may hear discussions about when we're talking about climate debates, modern climate debates, the discussion of, well, solar cycles aren't important because they don't change that much. But the fact is they seem to get magnified. So even though in the visible light range, that may be true, when we're talking about, say, the ultraviolet, for example, the changes along the solar cycle can be on the order of 10%. And while we're still trying to understand all these things, they do seem to have effects on the Earth in indirect ways, like causing changes in the amount of cosmic rays that reach the atmosphere, which may have an effect on cloud cover. Ultraviolet changes seem to have an effect on stratospheric temperature, which has an effect on climate. Then there are also long-term climate cycles, and I've only listed one particularly notable one there, the Maunder minimum, which is more of a long-term cycle on the order of a few hundred years. But there are actually many solar cycles of different lengths from hundreds to thousands of years. Overall, the sun, as I think most of us probably know, is the most stable star that we know of, even for solar type stars. But its short-term climate change is likely to come from other sources rather than from direct changes in solar output. All right. I think we've also at least heard the terms eccentricity, obliquity, and precession. So these refer to the orbital dynamics of the Earth. And this is Milankovich's theory, which was essentially saved in the 1970s when these patterns were discovered in various isotopes. And I would say that the most important of these is obliquity, the tilt of the Earth, which varies from about 22.5 degrees up to a little over 24 degrees on a cycle of about 41,000 years. Precession is probably the second most important. It involves the timing of the seasons. Essentially, is the Earth pointed toward, or is your hemisphere that you happen to be in pointed toward or away from the sun in winter or summer or spring or fall? That has a difference in the magnitude of the seasons. So right now, the magnitude of the seasons in the northern hemisphere is actually at its lowest because our precession works out so that we have a milder winter because we are well, I'm sorry, I'm getting that mixed up, but eccentricity, we're closest to the sun during winter, so that makes our winter milder. But eccentricity is really the least impactful of the three of these factors when you look at solar radiation input. All right, but here's something very important I want to point out here, because we often hear about 100,000 year glacial cycles. So for the last 2.5 million years, partly due to orbital dynamics that we were just talking about, the Earth is going through glacial cycles. And this has been happening, it's probably happened well over 25 times in that 2.5 million years. But we often hear about 100,000 year glacial cycles. Well, it's pretty well accepted that before roughly 800,000 years ago, what's called a mid-Pleistocene transition, glacial cycles occurred in sync with obliquity and on the 41,000 year cycle. But then seems to have changed in some way after that. And it's often stated that glacial cycles occur on 100,000 year cycles, but that's not in sync with eccentricity, but that's not really completely true. It is true that the ice cycle varies on that scale. In other words, ice gradually builds up on the Earth until it reaches a maximum, which is eventually basically climatically unstable. And then everything melts and the clock resets. And that's roughly 100,000 years. But in terms of interglacial warm periods, it is not a 100,000 year cycle. So as you can see here, these are all of the warm periods named by their geologic paleoclimate name. So MIS 5E, for example, is the Eemian, the last interglacial period. But what you notice there is that these dates since the last interglacial are nothing close in general to 100,000 years. In fact, the average is around 73,000 years, but the most frequent number is close to 82,000. Notice that 82,000 is twice 41,000. So what's really seems to be going on here is we have warmings during glacial periods that don't obtain the warmth that we would call an interglacial warm period. So as the Earth has gradually cooled over the last few million years, it's reached a stage where not every obliquity cycle produces a warm interglacial. And sometimes it takes 2 or 3 cycles of ice buildup for everything to melt and us to have a true interglacial like we are in right now. So actually, in the last one, it took 3 obliquity cycles since the Eemian for us to have our current Holocene warm period. I also want to briefly point out here that water is a very unique substance because it is most dense at a temperature of 4 C. And therefore, when we go to the bottom of the ocean, we don't have frozen ice because ice also is, as a solid, is 8% lighter than water. So that's, again, a unique property of water, but that essentially allows us to have a planet that, where the ice can float to the top and be subject to melting from solar radiation. Also, salt water plays a factor in density as well. Surface salt water is typically 2 or 3% more dense than fresh water, but it can be as much as 5% more for deep ocean water under high pressure. So the reason I bring this up is because that has strong implications for how our global ocean circulations work. And so here you see the ocean conveyor belts. We have deep water formation areas around the Antarctic and also in the far North Atlantic. And it turns out this is actually the most ideal setup to cool our planet. So because of the ocean circulations and the atmospheric heat transport, the equator to pole temperature gradient is reduced by 40 degrees C. If Earth had no efficient heat transport mechanism, the tropics would be 14 C warmer and the poles about 25 C cooler. Now realize I am excluding a few other factors here that relate to circulation patterns in the Earth, but in a sort of a static Earth, that would be the case. So really, we would not have a very inhabitable Earth if we were under that temperature scheme. And also, transport of heat out of the tropics seems to be more important than transport of heat into the polar regions overall. And it's interesting also that Psalms 8:8 seems to refer to the paths of the seas, reminiscent of ocean currents. Another very important factor when it comes to climate in the past and in the present is the position of the continents. The current position of the continents is more ideal for advanced life. Radioisotope differences between the Atlantic and Pacific suggest that Drake's passage between South America and Antarctica opened about 40 million years ago. And this was really the last link in the chain that allowed the current and the atmospheric flow in the mid latitudes to be essentially very continuous and steady around Antarctica. And this actually creates a kind of an ocean pump, which enhances the ocean currents. And this has probably helped to cool the Earth on the order of 8 to 10 C in the last 50 million years. And I'm going to show you here in a few moments a few of the past climates and how they were different from today. Okay, so I'd like to bring you briefly to the late Carboniferous climate because it's really the only geologic age since the Precambrian, about 500 million years ago, to have had carbon dioxide levels in the range of what we've typically had in our modern epoch. The Carboniferous was also characterized by very high oxygen levels, which incidentally allowed, because of the way that oxygen circulates in an insect's body, this was the period when you had some really large insects, 2.5 foot wingspan dragonflies, 8 foot long millipedes, that kind of thing. Sometimes I think I would rather take my chances with the dinosaurs. But so this was the continental configuration at that time. You had continents grouped around the South Pole that helped create large glaciations and ice ages there. But tropical flows of water were somewhat restricted as far as east-west movement. And this is a period when many of the world's vast coal deposits were produced in the Carboniferous tropical regions there that you see in the green and the pink. Now, in contrast to this climate, which was about a degree or degree and a half cooler than our present climate, we have the early Triassic climate. And what's notable about that climate is you had the Paleotethys Ocean there that you see, the red arrows are shown there. And if you want to think of it, you could think of it as sort of an ancient Indian Ocean. So you had all the continents together at this point. And what's interesting about that is so here's the equator right here in this region, but and I don't really have time to go into an explanation of the global atmospheric circulation, but in the tropical regions, you have the trade winds that merge toward the equator. And so this is essentially bringing very warm air together. It tends to rise and create storms along the equator. And this band shifts north and south with the seasons. But what's important to note here is that all of this warm water doesn't really have anywhere to escape. It just kind of piles up here because of the tropical circulation patterns. And so we end up with a world that on average is 5 C warmer than today. And perhaps the tropics were as much as 4 C warmer. In fact, there's some geologic fossil evidence that suggests that tetrapods migrated away from this region toward higher latitudes because of it essentially was too warm there. And we had like something like 1,000 parts per million carbon dioxide in this era. In fact, except for the Carboniferous, most of the time since the Precambrian had higher carbon dioxide levels than we have today. And what I want you to see that's real important here, now this is the late Cretaceous climate, about 69 million years ago. So we still had Cretaceous dinosaurs roaming around. You're starting to see continents that are somewhat familiar. You had a much higher sea level at this time, so some of the continental margins were flooded. But what's really important to see here is that unlike today, we have a tropical current pattern that essentially allows the warm air, or rather the warm waters, to just continue circulating around the equatorial region. They're not really pushed toward the high latitudes like they are today. Why is that important? Well, because the equatorial regions receive more direct sunlight. Those regions are heated much more than the polar regions that receive very low angle and diffuse sunlight. And so there's a lot of buildup of heat along the equatorial region. And in a climate like this, you don't get the water exported from the tropics so that the heat can be released in the high polar latitudes. Why is the heat released there? Well, the atmosphere is less humid and it's easier for heat to be radiated to space in those regions. So the average global temperature at this time was 21 C, which is at least 6 C higher than today. And there was even a period in the mid-Cretaceous before that where it was as high as 27 C. So very warm world compared to today. But the important thing to see here too is that there's no what we call deep water formation areas where heat is released to space around Antarctica and in the Arctic. And that's partly because many of those pathways are blocked to get the water there. And you also see that we don't have that circular pattern available around Antarctica because we have South America is still basically attached and Australia is still attached. Conditions continue to be very warm after their Cretaceous tertiary boundary. So the Eocene, again, 6 C warmer than today, 10 C warmer in the polar regions. You still had that current that was able to more or less stay in the tropics. And there are actually some things about this climate that haven't been fully explained by climate models. Now, this is an important slide because all of the things that changed here about continental configuration are what really drove what gave us the world that we have today as far as climate. So, and I've got the dates kind of listed there for each one, but basically the opening of the Australian Seaway between Australia and Antarctica happened about 50 to 26 million years ago. The opening of Drake's Passage, I mentioned earlier, started about 40 million years ago. Then we had the closing of the Indonesian Seaway. So this helps block some of the longitudinal movement of tropical waters about less than 20 million years ago. The Middle East Seaway also closed around 6 to 7 million years ago. The Panamanian Seaway, one of the last ones to close, probably was completed by 2 million years ago. The opening of the Arctic Icelandic Passage up here in the North Atlantic. So now this is opening a way for water to come further north into the polar region. And then even the opening of the Bering Strait about 7 to 5 million years ago. It's interesting. It's important to understand too about the greenhouse effect in the atmosphere. Energy bounces between the atmosphere and the surface as much as 7 times before it escapes to space. And realize that the Earth is heated not directly by the atmosphere because the atmosphere is mostly transparent to shortwave solar radiation. So essentially, most of the solar radiation that reaches the Earth reaches the surface first. The surface is heated and then the surface heats the atmosphere from below. And much of that heat is retained because of greenhouse gases. Now, water vapor is the most important greenhouse gas, probably responsible for over 50% of the warming due to greenhouse gases. Carbon dioxide may be about 25%. And then we also have effects from methane, nitrous oxide, and other gases. But that's, so basically, when we're talking about climate change issues, we've always had a greenhouse effect and the Earth is habitable because of it. And that greenhouse effect is on the order of 33 C. So without it, our surface temperature might be 0 Fahrenheit or minus 17 C. So when we're talking about climate change, we're really talking about how much are we adding to the greenhouse effect. Also, it's important to realize that when I was using that example a while back about the equator being so much warmer and the polar region so much cooler if we didn't have heat transport, that wasn't considering the fact that the Earth is not a radiative only system. It has a dynamic atmosphere that transports heat from the surface to space kind of like a boiling pot of water. And so this may account for tens of degrees of cooling as well. I want to briefly mention here too that there are certain wavelengths that the atmosphere absorbs carbon dioxide. And once those wavelengths become saturated, you can add more greenhouse gases or more carbon dioxide, but you won't really get much additional effect. So there is a point at which it becomes saturated. Now, I've heard some on the climate skeptic side say, well, we're basically saturated, and so we can't, adding more CO2 isn't going to make much difference. Well, there's some truth to that, but there's also some truth to their opponent's side saying, no, there are ways that the Earth can continue to add heat for additional CO2, because when you're, for instance, with CO2, when you're considering warming of the atmosphere, you're not just considering what's going on here at the surface, but you have to consider what's going on in the entire atmospheric column all the way up to space. So while the surface is close to saturation, there are, say, higher levels like the mid-troposphere that are not saturated. And I don't really have time to go over these in much detail, but just to say that what these charts are basically showing is that is essentially the warming that occurs because of CO2 in different parts of the world. So those are the tropics, and you see a similar situation for the subarctic summer, but then not as much for the subarctic winter. This slide is important to show you because it shows you that climate factors are a lot more than carbon dioxide. There are many radiative factors that contribute to warming. Methane, another greenhouse gas, and these values are all in watts per meter squared. Shortwave albedo change, so that's changes in the reflectivity of the Earth's surface. Tropospheric ozone, another greenhouse gas. Addition of aerosol black carbon on snow and ice, so that allows snow and ice to melt more quickly. There are also aerosol effects and glaciation effects and even solar influences. And when you add all of this up, what you find is that the CO2 contribution to radiative warming decreases to less than 30%. So, I bring this up to point out that, if we want to affect climate, we can't just focus on one thing. It seems like in the popular media, you hear a lot about CO2, but you don't hear a lot about these other factors. So this is basically a chart showing about the last 120 million years and the approximate global temperature through that time. And you can see that it ranges from anywhere from 5 degrees C cooler than today, such as during the last ice age, up to 12 C warmer than today. But there are limits to the variations of the Earth's temperature range, and this seems to be related to continental configurations and ocean currents that I've already talked about. I've also put on this chart a few of the major asteroid impacts, which seem to have some influence on helping in essence, enhancing the climate change that may have already been happening. So right around 35 million years ago, we have major asteroid impacts, and these were on the size of about 100 km to 80 km craters. So that's compared to the 250 km crater that was created by the dinosaur killing impact of 65 million years ago. So these are still pretty large. And these coincide with about the time that the Earth cooled enough for Antarctica to begin to become glaciated. And it's believed that actually happened in a pretty rapid period of, say, about 80,000 years. And this process was completed in about 400,000 years. Since the time that Antarctica has essentially had a major ice sheet, the world has never been warmer than about 4 C warmer than today. 17 million years ago, we have the Columbia River basalts, all those volcanic eruptions in the Pacific Northwest, and then as the Earth cooled further, and the Panamanian Seaway closed, we kind of entered the climate system that we have now. And there were some asteroid impacts as well, somewhat smaller than the ones 35 million years ago, but still significant. And it was at that time that the Earth entered into the present Ice Age epoch. Even though, we are in what we would call a warm period right now, we are still in an Ice Age climate. And what I wanted to show you here, this is a very interesting chart because it shows you that at least on a geologic scale, carbon dioxide is not always a good predictor of temperature. So this chart is essentially divides the periods of time basically since the dinosaurs into about 6 different climate regimes: the warm house, the hot house, cool house, and ice house climate. And we're actually in the ice house glacial climate, which is represented by this dark blue here. But notice in some of these warm climates that occurred in the past, you had carbon dioxide varying from as little as less than 300 parts per million all the way up to 1,000 parts per million. And with not a great deal of difference in temperature. Even for the cool house climate, the light blue there, that's really since Antarctica became an ice sheet, you had a pretty wide variation in CO2. And again, that's probably got to do with that saturation factor. If you go from 200 to 400 parts per million, you're going to have a decent amount of warming caused by that CO2. But if you then go from 400 to 600, you're going to have some warming, but it's going to be much less than the warming you had from 200 to 400, because addition of CO2 is essentially a logarithmic function that decreases with the as you increase the amount. Now, if looking at our current ice house climate, we can see that really the temperature is about as warm today as it's ever been in that climate. Now realize that these are 10,000 year periods used to create this graph, so we may not be able to extrapolate that down to a short period like 100 years. It's also very important to think about sea surface temperatures when we think about global climate, because today there's essentially a limit on sea surface temperature, and that's because the current oceans exhibit convective feedbacks. So once you get up to tropical sea surface temperatures like above 26 C, if you continue to warm up to above 30 C or more, then you get so much moisture being evaporated and clouds forming and rainfall forming and then clouds reflecting energy back into space, that there's kind of an upper limit on sea surface temperature of about 32 C in today's climate. Now, again, there's a debate between the skeptics and the people more on the alarmist side, because some will say, well, that's the hard limit, and so therefore we can't get the Earth much warmer than it is. But then others will say, well, no, that that limit has adjusted upwards in past climates. And I think there's some truth on both sides of that issue. So if we go back to the warm Cretaceous we were talking about, you had some tropical sea surface temperatures getting up to 35 C, definitely warmer than today. In the Eocene, 33 C. So I think that's evidence that it can adjust upwards. But I think it is also encouraging if you're thinking, well, how much can the world warm? How much can we have a runaway climate? 35 C is only 3 C warmer than today's maximum. And that's, in a climate that was, at least in terms of air temperature, much warmer than today. So I think that's somewhat encouraging that you may get an adjustment upwards, but it may not be a very large adjustment upwards. But under the current continental positions, maximum open ocean temperatures have always been basically 32 C. Now I'm talking about open ocean temperatures. They're not, in some isolated bay, like say some part of the Persian Gulf or something. All right. I think it's worth also pointing out that in the last interglacial climate, we actually had a period of several thousand years that was a couple of C warmer than today. For example, you had hippos living in the River Thames in England at that time. And the Greenland ice sheet started off actually 280 meters higher than it is at present, but it melted down to about 130 meters lower than present. And this was in a period when Greenland temperatures peaked about 8 C above the mean of the past millennium. This caused a sea level rise along with a 4-meter contribution from West Antarctica of about 5 to 6 meters. So what I'm basically saying here is that during the last interglacial, 35% of the Eemian of the Greenland ice sheet was lost versus today. So it doesn't appear that even in warmer temperatures that you completely lose the Greenland ice sheet. Probably today, the glacier that people are most concerned about is the Thwaites Glacier region in West Antarctica. The concern is that it will become unstable, and if it were to completely collapse, it would add about 0.8 meters of sea level rise. But it did appear it has survived the early to mid Holocene, our current warm period, where it was about 1 degree C warmer. Okay. I just want to briefly point out here, and I don't have time to go through the whole complexity of how you start a glacial because there's about 17 steps there. But here are some of the important factors. And this is something that Dr. Ross has discussed as well. The Arctic Ocean, actually, as it warms, it may eventually allow for the increase of snowpack. And when the obliquity decreases and the tilt of the Earth decreases, this eventually allows snow and ice to survive the summer. And it's really summer coolness that's more important for starting a glacial than winter. And the red here represents ice. So in the beginning of a glacial, the ice begins to expand. The permanent ice begins to expand beyond Greenland and cover areas around Baffin Island, Canada, and northwards. This is Baffin Island right here. Also, glacial periods tend to start when the perihelion, in other words, the closest approach of the Earth to the sun, is in the fall or the winter. Well, right now it's in the winter. Freshwater influx in the Arctic Ocean because of increased snowfall precipitation around the Arctic Basin allows for sea ice to more readily form because fresher water will freeze at a higher temperature than salt water. And this eventually results in circulation pattern changes that create a high pressure zone over Greenland, and eventually you end up with perennial northeastern Canada snow cover. Models have suggested that once this happens, because of the greater albedo, this can result in a decline of incoming solar radiation of 48 watts per meter squared. That's huge because, we're talking about modern climate change. We're talking about imbalances of 2 to 3 watts. And this increases the temperature difference between the poles and the equator, and that drives, although it drives a weakening of the Atlantic ocean currents up into this region, which allows the region to cool, it also increases the atmospheric moisture transport because of the stronger temperature gradient to the polar regions, which continues the feed of moisture into the area and thus snowfall and the buildup of the ice sheets. Okay, let me move along here. Okay, so I'll briefly talk about climate in the context of humans and human origins and human migrations. So I think if you're familiar with RTV's views on things, you know that the Garden of Eden was probably in the Persian Gulf. And if it was in the Persian Gulf, then that means it was during a time when the Persian Gulf was dry. And this happened many times during the Ice Age. These three horizontal red lines, if you extrapolate them across the map there or the chart there, anything below that. So this is essentially a sea level, global sea level, but it's very much also correlated with temperature. So lower sea levels are correlated with cold temperatures and higher sea levels with warm temperatures. So here's the Holocene we were in today. Over here's the Eemian warm period I was just talking about. So you can see there were periods where there certainly was water in the Persian Gulf, and so it's not likely that Adam and Eve would have originated then. I don't have the areas here blocked off simply because we're very aware of the existence of human fossils after that period, so it's unlikely would be in that period. But prior to that, there are several possibilities there, depending on how you look at various fossils and dating. I would love to figure out when the flood was, and there's certainly probably a lot of candidates, but the problem is we just don't really have enough information to nail a date on that down. It would seem likely to me that it probably would occur at a time when there was rapid climate change, but if there's anything about a glacial period, it's one of rapid climate change. The climate was far more variable in the glacial times, and that's typical of a glacial climate. But it is interesting that there were we know about human migrations during periods when the climate became harsher, such as this period between about 70 and 55,000 years ago. So we had a really cold period then, almost as cold as the one about 20 to 30,000 years ago. There were some interesting events that occurred during this period. We have the Toba super eruption around 74,000 years ago. We know that there seems to, at least based on fossil evidence, a very dramatic decline in human population after that. Now, to give you some scale, if you've ever studied the Yellowstone hotspot, you know that its largest eruption was about 1,000 times that of Mount St. Helens in 1980 in scale, and this Toba super eruption was about 2 to 3 times that of Yellowstone. There was another super eruption in New Zealand during the cold period about 26,000 years ago. There's also a magnetic event anomaly that occurred about 42,000 years ago. I didn't have time to show it, but what's interesting is there seems to be evidence for human occupation in the area of Israel up until about 70,000 years ago, when this major climate reversal happens. Then the area becomes occupied by Neanderthals, but they disappear somewhere around the time of this magnetic reversal. And then you see humans show up in that region again. To my knowledge, there's no evidence of any Neanderthals after this cold period here or after this super eruption. This is just another chart that shows climate instability during the last ice age, and essentially those horizontal red arrows or vertical red arrows are the brief periods of time when you could have had widespread agriculture. And so it's not surprising that we don't see large-scale agriculture show up in the archaeological record until, say, the last 10 to 15,000 years, because the climate just wasn't stable enough to support it on a large scale. But even in our what's often called stable Holocene period of the last 10 or 11,000 years, there are even climate anomalies there that have been significant enough to cause issues with human civilization. So I've just got a few of the major once pointed out there was an event around 8,200 years ago, probably associated with the draining of Lake Agassiz, which was associated with the last melting of the Laurentide ice sheet in North America. And then we have the more recent, what's called Little Ice Age, that ended in the 19th century. And looking at this again in another way, there's the 8,200 year event. There was also a 5,900 year event, which was the end of the African humid period. So up till 3000 BC or so, the Sahara Desert was not the Sahara Desert in the way that we know it today. It was more like a grassland and a scrubland, and maybe some of it was semi-desert, but it was occupied by humans who hunted animals. And when that period came to an end, you see the African humid period distinguished down here in the green, then that is when humans significantly occupied the great river valleys like the Nile and the Tigris and Euphrates. And really that's when the early human civilizations that we think of in history really got their main start. And then toward the more recent times, we have several warm periods that were favorable to human expansion, such as the Roman warm period, which is really centered right on the time of Christ. But we have that interspersed with some relatively cold periods, such as we've already mentioned the Little Ice Age, but there was also an antique Little Ice Age around the 6th century AD. And even in our stable Holocene, as we like to think of it, these minor changes can affect climate in a major way, at least a major in terms of human thriving. So what caused the African humid period to end was basically orbital dynamics. The obliquity, the tilt of the Earth is declining from its high of over 24 degrees. It is now down to 23.42 and declining. And that is having an effect on how north and south the intertropical convergence zone, which is what the ITCZ stands for. That's where the trade winds merge, but they're responsible for bringing monsoons north and south. So before roughly 3500 BC, you had it moving far enough north that it brought rain to the Sahara and more rain even to Southern Asia than today. But now at the bottom of this chart, you see this is where we are today. The ITCZ doesn't move as far north, and therefore the monsoons do not come as far north. And this has dramatically changed the climate in much of the tropics. So briefly, there's a chart showing the difference between vegetation in Africa 6,200 years ago versus today. The bright orange is the desert Sahara. The yellow over here is grassland, and the light orange is semi-desert. Now I'm going to try to hurry along here because I want to put a little biblical context on this. If we believe Abraham to be born somewhere around the mid-1900s BC, which is where this arrow is, his life and his culture was very strongly affected by climate. The worst drought in the entire Holocene in the last 10,000 years occurred in the hundreds of years leading up to his birth. And it's in these two dark gray shaded areas you see here. The first one lasted over 100 years. The second one lasted nearly 300 years and ended about the time of his birth. The dust record for this period, which is observable in tropical ice cores, just simply goes off the charts. Now back to the Dead Sea I mentioned earlier. Because of the way the Dead Sea drains, we can use it as a long-term rain gauge, and we know from its decline and rise in water levels that there were wet periods and drought periods. And the Bible mentions many droughts in the time of Abraham, Isaac, Joseph, and so forth. And so you can see that the levels of the Dead Sea were clearly declining during this time, and so that agrees with the biblical history. Even in the time of the Exodus, they were still declining. But what's very interesting here is they rise around the time of the conquest when the Israelites entered Canaan. So I'm going with the early date here of about 1400 BC. So in other words, the climate was very favorable because we know the Dead Sea was rising, therefore it had been favorable to agriculture. So if the Israelites had come any sooner to the land of Canaan, it would not have been the land flowing with milk of honey. It would have been the land of drought. But because they came when they did, you see the climate is much more favorable then. And there's actually many other events in the Old Testament that correspond to the beginnings of droughts, such as the migration of the sea peoples from the region of the central and Mediterranean, probably Greece and those areas. Some of those people became what we know as the Philistines. David's famine again correlates to a beginning of a short drought period. Elijah's drought, same thing. And even Judah's exile in 586 BC. The only one that didn't correspond to a drought is Israel's exile by Assyria in around 722 BC. In more modern times, we see similar climate patterns. So right here is the Little Antique Ice Age around the 6th century AD. And then this other light blue area is the Little Ice Age. And then we see the medieval warm period in between, and then our current warm period over here. But just to give you an example, during the Little Antique Ice Age, look at all of the climate, or rather the historical events that happened that probably had, certainly were influenced by climate. And probably not the least of these is the rise of the Arabic Empire and the spread of Islam. So if you think about it this way, a lot of these countries that were being conquered by the Arabs had been weakened because they were essentially in a period of drought caused by the poor climate at this time. So just to kind of wrap this up, what are some possible paleoclimate indicators that we've seen for the future? Many have talked about the shutdown of the AMOC, which is the Atlantic multi-decadal, or rather the ocean current. This works on scales of decades to centuries. If it does slow down or shut down, it probably won't shut down. It's more likely to slow down. You would end up with actually a cooler North Atlantic region, a cooling Arctic, more Mediterranean area drought, more South Asian drought. In thousands of years, the Antarctic cools. There's actually parts of the Antarctic that are cooling because the high elevation areas actually seem to have an inverse relationship with CO2. More frequent El Nino conditions, which would mean a mild, wet south in the U.S. winter, and occasionally a wet west coast. But the asterisk there is to point out that while the last 200 years on the west coast have been relatively wet, if you look at the last 2,000 years, most of it has been drier than today. Probably not much change in the Sahara Desert, and possibly a modest sea level rise on the order of a foot or two. And a somewhat faster hydrologic cycle, which could lead to some additional flooding. Continued greening of the earth. The earth has greened quite a bit due to the additional CO2 in the last 75 years, which has actually raised crop yields. Even if we had a way to instantly take CO2 back to 280 parts per million, which is what it was before the Industrial Revolution. It's currently at about 410 parts per million. I don't think I would want to take it all the way back there because it would have a negative impact on global crop yields. But I don't really think this is going to delay the next glacial inception. We're actually almost due for the next glacial. And without exception, over the last 800,000 years, when the tilt of the Earth has declined below 23 degrees, because that lowers solar radiation in the polar regions, we have started a glacial. There are other factors involved, like I mentioned, like the timing of perihelion, for example. But we're going to reach that 23 degrees in about 3,600 years. And we'll have that ideal precession value for at least 4,000 to 5,000 years. Now, there can be up to a 6,000 year delay when a glacial starts, just like when we have our seasons, even though, the peak tilts toward the sun in the summer in the Northern Hemisphere is on June 21st. We don't have our warmest weather until usually a month later. It's the same thing with glacial inceptions, but on a much slower scale. So what we could be suggesting here is that we might be entering a glacial sometime in the next 2,000 to 6,000 years. So even if we do have global warming, we're not, that's more of a short-term thing. It's very unlikely to prevent the next glacial. Now, there are some people who disagree with that, but frankly, I just don't see it, at least from the research I've looked at. And you have to realize that a lot of these things we talked about have very different time scales. The El Nino, otherwise known as ENSO, is probably affects things on a very short time scale, 3 to 7 years. It affects tropics, mid-latitudes, even the polar vortex. Volcanism can affect the transport of heat to the polar regions. The Atlantic multi-decadal oscillation, and I didn't talk about the PDO, but that's a similar oscillation of sea surface temperatures in the Pacific, can affect transport to the poles and radiation balance. And that's probably also true for anthropogenic effects. On the scales of centennial to millennial, we have solar impacts and possibly anthropogenic. We don't know yet, really. Multimillennial scales is where the orbital dynamics really come in. And then plate tectonics really comes in on the scales of millions of years. And I am sorry I ran over about 10 minutes, but that is, I promise you, that is the brief version. And I'm happy to take questions.
So I have a question for you.
Sure.
So what is your opinion on how much of an effect current climate is based on anthropogenic influences? And secondarily, how effective do you think any of the current policies are for making any changes to anthropogenic influences?
Okay, well, okay, let me start with maybe the best way to answer the anthropogenic influence question is to talk about those RCPs, representative concentration pathways I mentioned to someone before the talk began. A lot of times when you hear about climate scenarios, you hear things like RCP 2.6, RCP 4.5, RCP 6, RCP 8.5, and essentially what those are different climate scenarios that have varying magnitudes of impact. So RCP 8.5 is sort of like the worst case scenario. We're all going to die tomorrow. Unfortunately, that seems to be the one that people often compare to when they're doing modeling studies and outcome studies. And, when we look at observational data that we have, it just appears that RCP 8.5 is just not realistic. It's not pie in the sky, or it is pie in the sky, in my opinion. And so I really think that RCP 4.5 is probably much more realistic. And maybe RCP 6 should be used as kind of the absolute worst case scenario, although I really don't think RCP 6 is as low as what we're probably likely to see. So in terms of a percentage, I would be reluctant to say, oh, it's 60% anthropogenic and 40% natural, or, it's because there's so many different ways of looking at it. But, just, we were talking before the presentation started that, on average, if you put all the ensemble of all the climate models together, on average, they're probably running about 2 times more than what we see in the observations. So yes, there is warming, and yes, there is an anthropogenic influence, but it's likely not as great as what is sometimes presented. Now, as far as the political side, that gets really dicey. I work in a place around a lot of climate scientists, and I can honestly say that they are great people doing great research, and they're, individually working on their own parts of the puzzle, and they're trying to make the models better. They're trying to understand the climate system better, which is a really a huge task, because as I think you've probably seen from this presentation, the climate system is really complex. But I think the problem with politics really comes from people at a higher level, and not always, but often they are people who are not directly tied to the science. But I can say from experience of 30 plus years of being around this, it's very hard to do science when something becomes politicized. It's really quite challenging, and I'm not quite sure how to solve that problem at this point.
Yeah, I guess I was asking less about the politics, because I think the politics are also a big issue, but more about the solutions that are being purported to solve it. Are they really influencing the climate at all, or are these just solutions that are spinning wheels?
Well, I did a presentation down for the RTB folks down in San Diego a while back, where we looked at some of this in terms of energy, and it's because of the nature of the politics. I think it bleeds over into the policy issue. So, in my opinion, if I were going to try to reduce our impact, I would be going, it's not that I don't care about CO2, but a lot of those other factors I mentioned are lower hanging fruit, if you will, and easier to deal with. It's like, for example, I never hear anybody talking about changing the albedo, the reflectivity of urban areas. A lot of the warming that's been observed is because of urban heat islands. That's a human impact, but it's not greenhouse gas related, and you never hear anybody talking about that. A lot of these policies just are a little bit short-sighted, and because they don't seem like they think through everything. Like, let's take wind and solar, for example. I've got nothing against wind and solar. I would happily put solar panels on my roof, but they are the most diffuse form of energy collection out there compared to all the other major forms of energy, nuclear, coal, you name it. And it's just not going to be able to scale up to the point to replace the power grid. But I don't hear a lot of talk about how do you address that issue. I think somebody's got their hand up there.
I've got a two-point question for you. This is Lothar Kleiner.
Yes.
And one is that there are quite a few benefits for an increase in carbon dioxide, especially for the trees our produce becomes more efficient because they need less water because of the way the pores react. So actually some of the places that are close to the desert may actually be greening if we had a little bit more carbon dioxide because they'll need less water.
No, that's absolutely true.
The other thing that really worries me is this electrification with these Tesla, for example, needs about 11 kilograms of lithium. Wind turbines need 4.7 tons of copper. And if you look at all the rare earth metals that are required for these magnets, you have to move tons and tons of dirt to harvest them. And those areas, especially lithium, are in arid areas where you need 500,000 gallons of water to get 1 ton of lithium. And now you want to multiply all the wind turbines and the electric vehicles and so forth. It's going to be an environmental catastrophe where the mining is occurring.
I don't disagree with that. That is in agreement with the research I've seen.
Thank you.
I think Ron Martin has his hand up.
Yeah, it may be more practical to replace automobiles with public transportation rather than with electric cars. But anyway, my question was that did I correctly draw from your presentation that conditions favorable for agricultural will return after we depart those conditions? It'll return in about 4,000 years due to the changing of the Milankovitch factors?
Well, what I was saying there is that, while it's still unclear how long our anthropogenic impact might be, but it does seem pretty clear that we're not that, in terms of thousands of year scale, we're not that far away from the next glacial inception. So I think we would prefer to have the climate we have now, even if it's warmer than expected, versus a glacial climate. Because a glacial climate, yes, there are places on the world where people would survive and thrive even in glacial climate, but not anywhere close to the numbers that we have today.
Well, Hugh Ross, in his book Weather and Climate Change, says that with global warming and warmer poles, there will be a lot more rain coming out of the poles, and the clouds will move south with all this water. And he said that it would create another ice age due to that. So is that a factor bringing out an ice age?
Well, I think I sort of alluded to that when I was talking about the glacial factor. So it would essentially, the factor there is having the Arctic Ocean warmer, and it would create more precipitation. It would actually increase snowfall around the Arctic areas. But the key region is the region up there in Northeast Canada next to Greenland. When that starts to have perennial ice and snow cover, then you can get the beginning of the glacial. It goes from there. But it's not real clear to me if it would happen just on account of increased precipitation. That is a factor. There's no question it's a part of it, but there are other factors as well. Now, you can have a glacial inception with the tilt above 23 degrees, but there have to be other cooperating factors like what precession is doing, because that affects solar radiation in the polar region, and I already mentioned the timing of the perihelion, and there's really quite a few factors.
Yeah, Hugh
Okay.
Ross is the only person that I've heard saying that more carbon dioxide is going to lead to another ice age, maybe more glaciers in Yosemite Valley or something.
Well, I'm not saying that it's going to lead to an ice age, but I'm just saying that the time scale of our influence is pretty small, even if it's hundreds of years, compared to the scale of the orbital cycles and initiating the next ice age. I mean, whether we were here or not, that would be the next thing happening, the next big thing happening. I think John has had his hand up for a long time, and
Yes, yeah. Can we go to the next question?
sure.
Yeah, this is John Yu. So I think my first question, which I have it in the chat, is a clarification of the conceptual idea. I think we touch upon that in the last question. The glacier inception in the next 2,000 to 6,000 years. Conceptually, what are the primary mechanism behind that? I'd just like to hear a clarification of the major concepts. You know, I came away with the fact that the tilt of the Earth axis is gravitating to below 23 degrees, and that's the primary mechanism. But then there's another mechanism is global warming, the warming of the waters, and that then promotes more precipitation in the Arctic, the Greenland, and northern Canada area, which then triggers the glacier. Is that correct, or am I missing something else? So that's the first question.
I would consider the tilt, the obliquity as the primary factor, but I would say that the precipitation is more of a secondary factor that aids it. Another one is precession, the timing of precession. You know, you want to end up with summer solar radiation that's lower, and that can be influenced by not only obliquity, but also precession. Eccentricity affects it as well, but like I said, it's probably a factor of 10 less than the others.
Okay, that's good. So the obliquity factor is a natural phenomenon through the
Yes.
ages, right? So
Yes.
there's nothing men can do about it. And so the carbon dioxide and global warming is just a perturbation on top of that, right? But to sort through how much factor or how much weight you can put on obliquity versus the man-made CO2 warming, could you sort of put a estimate on that by percentage? Is it like 80 to 20, 60 to 40?
We have thrown up, I've had those discussions with RTV folks for years, and I still, you know, after all these years, it's really hard to pin it down. I would say, it's definitely not 100% one way or the other, and it's probably not even 80-20 one way or the other. It's probably somewhere between those two, but whether it's 40-60, 50-50, 65-35, it's a little hard to say. There's
Okay, I will accept that. I mean, that's something.
maybe another way of looking at it is, I've seen a number of studies that have looked at the temperatures of the last 150 years since we came out of the Little Ice Age.
Mhm.
It seems pretty obvious that we would have, even without human influence, we would have expected some warming, because at least after the 19th century, because the Little Ice Age was actually anomalously cold for where we should be at normally in the Holocene. And the human influence does not appear to have been that great up to 1950. So we had something like a half a degree, 0.6 C of warming from 1850 to 1950 that I would attribute at least 90% of that to natural factors. If you talk about after 1980, then the human influence is probably a lot greater. Maybe it's half of it or more. I'm not sure the exact number, but maybe that's a better way of looking at it in terms of different decades. I think the human influence is definitely significant since 1980.
Okay, great. And the second question is it possible, you talked about the two models, RCP 8.5 and RCP 4.5, and you said that the RCP 4.5 is more realistic to what the data actually show. Is it possible for you to just describe the difference between the two models, and what does RCP 4.5 actually predict?
And while you're at it, Kevin, I think you said RCP is representational climate pathway. Is that right?
Representative concentration.
Oh, concentration. Okay. Can
I
you,
don't have any, I don't think I have a chart or like a world map handy. I think those are pretty readily available, but so, it's basically based on the fact that if you look at the observational warming that we see versus the modeled warming, it's more in line with those lower RCP scenarios like 2.6 and 4.5. 8.5 is, well, they used to call it business as usual. In other words, we just don't make any changes and we just keep growing and expanding all these fossil fuels and so on. And that's where we end up with RCP 8.5. But that's actually been shown now not to really be completely accurate. I think RCP 8.5 is even beyond business as usual. So maybe RCP 4.5 would be that we make some changes, or that the energy industry changes enough that maybe fossil fuels aren't as much of a factor. And certainly that's true of RCP 2.6. These are all defined in the climate reports that come out from the UN and the IPCC.
Okay, good. I think I have a pretty good idea. So, but the policy that the world and the UN is going on is based on the model RCP 8.5?
I would say that far too often, probably the majority of cases, that is true. When I'm always, because of my job, I'm always looking at the scientific literature, and when I see something that used RCP 8.5 as a comparison, I pretty much take it with a grain of salt. Unfortunately, most people don't do that, and they get the most sensational answers when it's compared that way. So, but I think if we want to be more realistic and we want to be trying to aim toward what might really happen, I would love to see more emphasis on some of those lower scenarios.
Okay, so lastly, so if one were to compare those two models, let's say the prediction of the delta of increase of a global temperature for model 8.5 versus model 2.6, say 10, 15, 20 years from now, what is the difference? Is it like 3 degrees versus 0.5 degrees or what?
It's probably more like 2 degrees versus 6 to 8 degrees.
So 8.5 would predict 6 degrees and 2.6 would predict 2 degrees?
My numbers aren't exactly right, but that's, the scaling is sort of like that. But I think normally we'd be talking about the temperature in the year 2100, not just a few decades down.
Okay, 2100. Okay, well, that's only 70,
yeah.
But 75 years from now.
But if you look at the last 40 or 50 years of observations, what you basically see is a global warming of less than 0.2 C per decade.
Yeah.
If you project that out, so we basically warmed from the bottom of the last ice age to now, maybe, the little ice age 150 years ago, maybe 0.9 to 1 C. If you continue to, let's just say optimistic, the high end 0.2 C per decade, 80 years, that's 1.6 C is what that is. That's far less. Now the rate could change, but so far it really hasn't. And even that 1.6 C, which is probably more on the high end from what I'm seeing, is still far less than, say, what a RCP 6 or 8.5 would give you.
Thank you. So this is consistent with what Patrick Moore has been describing in his YouTube videos.
Well, I've not really followed him, but there are a lot of people out there And yes, I don't know his background, but it can be a bit difficult to sort out good sources of information.
Mhm.
One
Okay,
person.
thank you very much. I really appreciate it. Thank you, Kevin.
All right.
Any other questions anybody want to bring up at this point? Well, so I would ask, I mean, if I don't see another hand, I'll ask a couple, because you mentioned your compatriots, your scientific compatriots there at the lab, and would you say that they're generally in agreement with you, or are they more aligned with the political forces in Washington, D.C.?
That's difficult to say.
Okay.
I mean, I'm certain that some of them would be aligned with the standard view, but I do run into more that have differing opinions than you might expect. Of course, you know, we really try to avoid. I mean, at least the folks in my group, we really try to avoid getting real political, but which is nice. But I think that's you know, I've always, one of the problems here is people tend to look at it as a two. You have two choices, and it's really not. It's really more of a spectrum, and so I don't think it would be, if I had to go through and categorize people in general, I don't think they would all like just fall in one spot over here, one spot over there. I think there would be sort of a variety of opinions about things.
If you had your way, if you were the king of the world, what actions would you take globally to address the issues of climate change, to reduce the effects of anthropogenic warming factors?
Well, I would put a lot more focus on non-CO2 factors, things like land cover change, other greenhouse gases like methane that are easier to remove from the atmosphere. I wouldn't stop researching on CO2, but you know, I certainly wouldn't put all my eggs in that basket. And then I think you know, the other part of it is kind of what we've already discussed, is unfortunately human nature, because even though there are some real issues here, human nature gets involved, and agendas get involved, and politics get involved, and then all of a sudden we're not looking at data anymore. We're kind of tilting things based on what our agenda is, and if the data agrees with our agenda, that's fine, but if it doesn't, then we tend to change it to something else, and it's just a sad, unfortunate state of where we are.
Kevin, on that topic of other ways to address warming, I believe a number of the national labs have been looking into cool roofs, and I suspect Oak Ridge has been doing that too. Do you know of any other ideas similar to that, to reduce the urban heat island and things like this?
There is I don't remember the name of the author, but there's a paper that came out about 5 years ago in Nature that talked about these nanospheres, that like glass nanospheres, and they were embedded in it like this plastic film, and supposedly if you put it on your roof, it'll cool it by something like 10 C.
Mm-hmm.
And the spheres are of such a size that they reflect radiation back to space at the right wavelength to go through the atmospheric window.
Mm-hmm.
I don't understand why I don't ever hear about this. Why aren't we like mass producing this and
Well,
putting it on all you know.
Yeah, I think at some level we are. Those shingles cost more, but that's what I had put on my house when I had it reshingled about 10 years ago. I had these cool shingles put on that they have some sort of glass beads in them in the surface that makes it very reflective in the infrared.
That sounds like it. You know, I've been involved in some studies, or hopefully am about to be, in dealing with some urban areas. And I didn't really mention this in the talk. I have in other talks, but some of the larger cities, you can, under the right weather conditions, you can have a artificial warming of on even as much as 8 degrees C. Say like a city the size of Atlanta or London. And that is something that really needs to be addressed, and a lot more emphasis needs to be placed on that. But yet you rarely hear about that in the climate change discussion.
I'd like to shift from political questions to theological ones. You're a minister, and you're in an evangelical denomination, and most, according to the polls, a good percentage of evangelicals, as well as other Americans and other people around the world, I guess, are looking at the world as being only about 10,000 years old. And there are various scientists with various institutes who are continually trying to present scientific data similar to what you presented here to handle that. I find it difficult to see how they take all the data that you came up with and squeeze it into 10, 15,000 years, but apparently they do. And they come up with answers to all this. And so the result is, I'm wondering, when you do address other evangelicals and so forth, do they just turn you off when you get beyond 10,000 years? And or do you just only stick to the last 10,000 in talking to them?
Most of the time I just present what I have. My denomination and some similar to it, while there's certainly been significant inroads made in the last several decades by several young earth organizations, historically they've really always had kind of a mixed view on that. And I think that's largely due to the influence of Finis Dake. The Dake's Annotated Reference Bible. He was actually my grandmother's first pastor, and he followed Schofield as far as his view of creation, and that was a gap theory view. And even though that's not RTV's view exactly, it is an old Earth view, and I think that's afforded me to find people who, most of the time, to find at least some people who were okay with going beyond 10,000 years. There certainly are some that would prefer I not, but it's always been kind of a mixed bag for me on that.
Have you seen presentations by the young Earth scientists that deal with all the phenomena that you deal with, and are in fact, are any of them, I mean, a lot of them have PhDs in biological subjects. Are any of them in geological subjects or climate change and so forth that you've heard about?
Well, I know, there was a book many years ago published by ICR that essentially attempted to explain the ice age as a result of Noah's flood. I don't find that presentation very satisfactory. That's probably the closest thing I know. I think Ken Wolgamuth could probably speak to a lot of that as well, but
he's got his hand raised.
Yeah, I've been following them with that, and in fact, I visited the museum that ICR just put in down in Dallas about 2 years ago. They basically don't even address all the data. They just say Noah's flood happened about 4,400 years ago, and it threw out so much volcanic activity into the oceans that it warmed up the oceans. And that triggered a lot of evaporation of water that built a ice age that lasted about 500 to 700 years, 4,400 years ago.
Mhm.
So it can be said that they're not really addressing the data. They're just making up something so that they can tell their captive audience a variety of types of sort of fake science that they say they're scientists and they do that, but their story does not fit reality. So it's sort of counterfeit type of material.
So apparently they follow the Masoretic text and not the Septuagint.
I don't know which one they follow.
Well, the Septuagint has an extra 1,600 years or so in it. So.
Oh, okay. Yeah. But to say the ice age is 500 years long is, kind of bizarre, because there's, 100,000 years of ice on Greenland and, 800,000 years of ice on Antarctica. So it's just counterfeit material. It's just fake stuff. It's just made up.
Well, I will add this to this conversation, and that is, over the years, I've had conversations with quite a few people who were young Earth. But I found that, and I know you can't always do this, but I found that it's better to, if you can actually establish a relationship with the person, then there is some hope of convincing them. I have a friend, I live in Jamestown, Tennessee, in a rural town, and I have a friend here who many years ago, I think, was kind of on the fence of this when I first met him, but he came around, and he's been a very ardent RTV supporter for many years now. But relationship matters. Actually, I need your prayers on that, because there's another church here in my town that has a man there who, well, let's just say I was shown his material that he was presenting to his church across town, and it was straight out of Answers in Genesis. I was really dismayed when I heard, even though I think this gentleman is a fine gentleman, he's actually an educated person, but I was introduced to him, and he's supposed to call me, and we're supposed to have lunch, but so far he hasn't called me. So we'll see where that goes, but it could be a long process, I'm sure. So,
And you're absolutely right. You have to try to build a relationship, and it's hard to do that unless you live in the same town or in some way can get together. I've invited myself, I don't know how many times, to try to go down to ICR, and they won't even let me in the door. So,
Well, I think we're wandering a little bit from our topic. So,
yeah.
and I unless anybody has any urgent questions they want to raise, I think I'm going to terminate this and
Kirby, I do
go
have
ahead.
one. We can ask in with the people here. We can ask offline. But I am interested in Kevin's comment on. I know you've given your presentation at the RTB Covina headquarters, right, with all the staff, Hugh Ross and Fuzz Rana, and so on and so forth. And I'm a little bit curious on the policy aspect, because in Hugh Ross' last book on climate change, and he touched upon policy a little bit toward the end of his book. And I think in one of the meetings, I asked him, well, what is the best way for RTB to influence the national policy in Congress? And I remember his response was through RTB scholar community. In other words, use an indirect method to influence the policy through people like you, Kevin, the RTB scholar community, And I wonder if you had that discussion with them, with the RTB staff, and if you could share some of that.
I don't think we had that specific discussion. I was a reviewer of the book, Weathering Climate Change. But honestly, that would be a little difficult for me right now because of where I work. I'm not really in a position to be able to be a political advocate, and maybe that might change. I mean, I'm not planning to work in that way forever. So,
I
but
see.
you know,
Yeah. Okay. So that's a concern. Yeah. Right. It's kind of like where does your money come from, and how much risk can one take?
well, I mean, we're just not supposed to really be a political advocate in our
Right.
position. So,
But RTB as a independent nonprofit organization could. And some thoughts that occur to me is that you know, this model that the U.S. has been embarking on is based on a false model, and they should correct itself. They should immediately look at the realistic model, which is, as you said, could be the RCP 2.6 or 4.5, but something that's more realistic. And so the Congress, if enough people in Congress is educated to see what this model predicts, then it would change the urgency that drives the policy.
So I have to jump in here because you've got all these scientific bodies, IPCC and the UN that are holding forth these more drastic models, I think, and I don't think our RTB is in a position to lock horns with those groups myself.
Yeah, RTB is not, but then, just think broadly, maybe some other, if you can convince a senator or Congress body or the National Science and Technology Board on the Presidential Commission to look at this thing more objectively, I mean, anyone with a realistic sense would say, hey, we ought to adjust our policy.
If I could interject a little bit here.
Sure.
I was Googling a bit to try to figure out what this 4.5 and 8.5 actually mean. And I came across a website. The first one that popped up was caladapt.org. It's a California state website to help groups that are trying to predict effects of climate change. And what they say is, if you want to be conservative, if you want to look at the worst case, basically, use this RCP 8.5. But if you want to be more thorough, use RCP 4.5 and 8.5 and do a scenario on either one, on both of them. And so they're doing kind of what Kevin is suggesting. They're saying to look at both the extreme scenario and what they call the medium warming scenario. And I was kind of pleased to see that they're actually recommending that. And by the way, the 4.5 means 4.5 watts per square meter of extra heat, and the 8.5 is the same in the year 2100.
I see. Okay, very good. So someone's doing something, but does 4.5 agree with the actual data?
it may be a little high, but it's probably close. I mean, we don't really know yet, but I think it's becoming more and more obvious that 8.5 is just out of the realm of realism, and it really doesn't, and certainly doesn't need to be used for making policy.
But it is driving the policy today, isn't it?
It's got too much of an influence, but the problem with doing, you could call that being conservative, but the problem is, as with anything, if you overreact to something, I mean, this applies in a lot of fields, you know, so like I've been involved in emergency response at my work for a long time in terms of like modeling accident scenarios. And if you say like, you know, some chemical was accidentally released and then we model given the current weather on it. If you be overly, let's say it goes over a nearby interstate, if you overreact to that and you say, well, I'm going to evacuate everybody in the 3 counties and shut down the interstate. Well, you know what? People are going to die because you shut down the interstate. There's going to be accidents. There's going to be all kinds of ramifications. And that's the problem is if you're too conservative, you know, people might say, well, I'm not doing enough and people are going to die. Well, maybe, but if you go too far the other way, you have the same problem. So, and it's true. I think it's very true of this issue too.
Mm-hmm. Yeah. Yeah. Sometimes, you know, a realistic model may be considered conservative, but I think if it is realistic, we should just say it's realistic, not conservative.
Yeah.
Well,
Kevin, I had another brief question. It's probably a big question, so if you could answer briefly, that'd be good.
Okay.
But what are your thoughts on climate engineering that I've heard about from time to time? Shooting rockets in the air to throw stuff up in the atmosphere and change the albedo or the reflectivity. Is there, to me, it sounds a little risky and crazy, but is anybody seriously thinking about that these days?
I think it's certainly doable. The problem, and I think people are starting to think about it a little more seriously again, but I think it's fraught with, you know, you do something and then somebody blames you for changing their weather in a negative way, and you know, it's your fault. That's the big problem with that.
Okay,
So,
thanks.
Nobody has mentioned the elephant in the room with, for example, RCP 8.5 versus 4.5. And by that, I mean, China seems to be going for broke and still increasing the amount of coal that they're burning, you know, and they're adding CO2 to the atmosphere at a much higher rate, an increasing rate. And, you know, and then there's India as well. And then there's also Africa, which has got all this developing nation with mass poverty, and people need to develop energy sources for Africa. And, you know, so it's almost like whatever we do in the US is not going to matter too much when we've got the rest of the world pumping out CO2 at an ever increasing rate.
No, I can't argue with that. I mean, it's a problem because you're not going to get, you're never going to get everybody on board.
Yeah, and I'm wondering if that's more like what 8.5 is geared towards. That is to say, that these other nations are not reducing CO2 at the rate we are. Or
Well,
is that wrong?
I think 8.5 is probably even beyond that.
Okay.
Yeah, and that was my question. Earlier, if I understood correctly, you were saying the max real conservative number that somebody should be using should be closer to RPC 6, correct?
I think so. Yeah. And
Okay.
I think the real is probably closer to 4.5 or a little less.
Okay. So that's helpful because, you know, going back to that California policy, then if it was going to be realistic, it should be looking at scenarios of 4.5 or less compared to RPC 6 at the most, and not the RP5 and RP 4.5, not RCP 8.5.
Well, one thing that factors into this that I didn't mention in this talk and is water vapor, because assumed in most modeling is that, you know, let's say you have a 1C warming from doubling CO2, and then you get a feedback from water vapor of 2C. So like a 3-to-1 ratio. Well, observationally, it's not real clear if it's actually that much. There's definitely a real water vapor feedback, and a significant one, but whether it's actually 3 to 1 is still out for questioning. It might be 2 to 1, it might be, so it's, if the water vapor feedback is not as great, then you don't get as much of a warming.
Okay, I'm going to take this opportunity since we're past 9 o'clock our time, and I know that it's at least 11 o'clock Kevin's time, and he actually sometimes is in Eastern Standard Times, or so it's even later for Kevin. So I think we need to cease this meeting. And Kevin, if you would close this meeting with a word of prayer, I would really appreciate it.
Sure. Lord, we thank you that we've had the opportunity to come together and discuss this, and we just pray that we can use this information to help foster truth in our community and help somehow, Lord, to bring people to the knowledge of your saving grace. In Jesus' name, amen.
Amen. Well, thank you very much, Kevin. That was a really great presentation. As I said, my head was swimming about halfway through it, and it got to practically underwater as the further you went on. So,
Well,
anyway,
thank you
thank you very
Kevin.
much. I appreciate that.
You're welcome.
I wanted more.